Hello and welcome to our weekly Dlubal webinar. This week's topic is construction stages in membranes with RFEM 6. My name is Jürgen Teilmann and I work for Dlubal Software in the customer support, and today I am your host. And while Andreas will be presenting, I will answer your questions. So by my side is Andreas Niemeyer, and Andreas, you can take your time to introduce yourself.
Yeah, hi to all. So I'm Andreas Niemeyer. I'm responsible for the product engineering here by Dlubal. I'm taking care about all new features, about the program concept, which features we implement, how we implement, that everything fits together. And today I'm the presenter of this webinar.
Yes, thank you, Andreas. So I take back the control for a second. We both switch off our cameras so the viewers can see the full screen. And just a few details in the beginning. So this is our new panel in the new GoToWebinar, in the new user experience. On the right corner, you have your panel. And on the top right, there's a small cogwheel for the general settings. And there you can adjust your audio settings as well. Like I mentioned, when Andreas will be presenting today, you can ask your questions. There is a small question mark in a kind of a bubble. If you click on that, you get to the question section and you can enter your question, hit send, and I will try to answer your questions as good and as quickly as possible. If I don't get to answer all of your questions, don't worry. You will get an answer per email. The other option would be to just enjoy the webinar today and send your questions via email to info@dlubal.com. So that's all from my side for now, and I will hand the control to Andreas. Andreas, the stage is yours.
Okay. So, thank you, Jürgen. Then I take over with the topic construction stages in membrane structures. A quite interesting topic, I would say, and I tried to make it interesting for you today for the next hour. I searched also for an example how I can explain you this complex stuff, and I found a pretty good example. You can see it here on these slides. I divided it in separate main points to lead you through this topic. At first, we make us together some thoughts about the structural task, what we want to do and how we change it during the calculation. Then we model this stuff in RFEM together from scratch. In the next, we take a look on results and why we should consider stages during the calculation. We analyze the special load effects in membranes. Point 3 and 4 is more or less one point, and we repeat it from stage to stage. And finally, I give an outlook regarding the fields of membrane structures in RFEM. So this brings me to the end of this slide, and we jump directly to the first point. What means the structural task? So here you see what we want to model in the next period. On the left side, we start with a double cone membrane with a funnel on the front or back, and the double cone is spin or supported with such a steel frame in the middle. Yeah, I would say a really nice structure, what contains a lot of stuff. I selected this structure especially to show you how you can work with the program, which functions are existing. And then we bring up a new scenario that, let's say, the owner of the structure decides that he don't want to have columns inside, and we should try to support this structure anyway, and we decide here for such an external arc. Yeah, and how you can do this in RFEM, I show you now. Oh, this means I show you now in a live presentation. I jump in live into the program and we start a new model. So for starting a new model, we create a new name. So I say WT6, for example. Of course, we select the 3D model and we take here the add-ons stages, construction stage analysis, and form finding. So this is, well, let's say these are the tasks what we want to perform in our calculation. And when I activate this means that the program is mutating in background, that I get at the relevant places the relevant options to change. Yeah. And now let's go in and we receive, let's say, virtual RFEM environment with graphical environment here, with spreadsheet on the bottom, with navigator on the left side and toolbar on the top. And yeah, here we can start modeling. So as you just saw in the presentation that we have here these double cones. So you can imagine that the double cones have the bigger diameter is a 5-meter diameter and everything is lying on the XY plane. And the height of the cones is 5 meter and the depth of the funnel is also 5 meter. And in top view, you can imagine everything is on a, let's say, triangle with the same length of boundaries. So now to do this, I watch on the top view, I close the table and we create here a line. What defines the triangle? Yeah? The triangle length is 10 meters and now we take this line and rotate it by 30 degrees and confirm it. And now we select line plus node, rotate it again with minus 60 around C and create a copy and directly say, please create me lines between selected nodes. And so we get a triangle with every side have the same length. The angle in between is always 60. And on this basic geometry, we can set up this structure what we want to model. I would say here the bottom points describes the axis of the two cones and this origin describes the funnel center. Yeah? So therefore we draw now here in this sketch 3 circles. The first circle of the funnel is 5 meter. Here also 5 meter and the last one also 5 meter. So this is the bigger radius of the funnel and cones. And now the smaller one, so for the cones we use 1 meter, 1 meter and 2 meter for the funnel. So basic sketch, I would say, what set up our basic geometry. Generally from drawing it's fine, but from creating a final element model, let's say you will see that you get some node-oriented nodes like here, 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 here. So if you expect later to have a nice symmetric mesh, it makes sense to orient such stuff. So for this, I select the circles here and here, do a right click on the selected stuff, edit here these lines and go here to circle and change here the, let's say, reference angle to 0 and confirm it, and you will see all nodes are oriented to the x-axis. So now we have, let's say, our basic sketch and we can start modeling the cones. Of course, you have to know if we watch into x-axis, we are still on plane. So this is still a 2D sketch, but we can make it 3D in the next step. So for this, we select again all circles, do a right click on it, lines, edit. Oh, sorry, not edit, then lines, divide, and with intermediate nodes, define here 5, confirm it, and now we get the circles divided in with these intermediate nodes, where we can draw in these, let's say, ray lines, what means we can model these cones by small, I would say, cake segments. Yeah. So this is now easy stuff. What I can do, I model only principally these cones by this, let's say, line construction or wireframe model. And you see, this is the double cone on the back. And now let's model the funnel in front. And connect simply the lines from the outer boundary to the inner boundary. Oh, here I forgot one. So this is now the basic shapes with the ray lines. Here you see I had some gap. If something happens like this, I connect it simply. And now also we should model these boundary cables around. So this is again a really easy task. So we connect simply these basic nodes with lines. So it looks like a chamfered triangle finally. And in the next step, we can bring in the 3D effect. What means we select this and these nodes. Deselect the center node, and now we take this selection and move it -5 meters in the top. Yeah. So okay, and the same we do for the funnel. So we select this without the center node, open here the move and copy function, and now let's move it 5 meters in the bottom. And if we watch now the X graphics, you see directly with these ray lines that we have now here these two cones principally, and the funnel on the front principally, what we want to model. So now you can ask, of course, why I'm drawing this so, let's say, stupidly with these rough lines. This is my, let's say, my target. So I try to simulate this structure in a really rough way to define only the boundaries. And my main target is to draw or to create a model what could be meshed and what looks roughly like this what I want to do, because the real optimal shape will be found by a computer process. So I cannot model it, and I don't want to waste time with it. I only want to waste time by modeling the structure so rough as possible in the space. What allows me to mesh it with flat mini surfaces. Oh, here let's say I don't touch the node. And later I say the computer or the RFEM, please find me optimal shape. So now we defined the shapes for the two cones. Now we close it with the funnel shapes. So here again, I have to draw it here to this node. And now let's bring in the final remaining ray lines, and I would say this was now the definition of lines, and we can go over to the definition of surfaces. So really rough, really sharp edged, but this is no bigger issue at this stage. Now let's define surfaces. For this, I use here this quadrangle surface type, because quadrangle is a biaxial curved surface and the shape within the lines is defined with its boundary lines. So it's no form finding condition or something else than a pure geometric job. For this, we take here a thickness from PTFE material. You see, this is a fabric material type, would have already orthotropic elastic stiffnesses, and these stiffnesses are referenced to 1 millimeter. And we use a membrane stiffness, what means it's a surface what can only take over tension, no bending. And now we start defining these stiffnesses within these lines by clicking the, let's say, the boundary lines in graphics. Yeah, and you see this is quite easy job. Yeah, we pick purely only these lines. So of course you need some concentration for it. Nope. And now I see it. Go, and the back is already finished now. Now let's jump to the front. And now here, oh, quadrangle, okay. So here this is a geometry what is changing from the top cone to the funnel. So, but this quadrangle surface is interpolating its shape in between. Nope. And here, and now we can change to the center. And now here with this line surface, we close the left cone. Oops. Here we have again the symmetric shape to the left one. Exactly. Now we finish the right cone. And here we find the last gap. Yeah, we pick here again these lines. And you see, it's get colored, and we get what I expected, a really rough model of this shape what we want to model. Yeah. So now these surfaces are defined, and of course we want to modify it later to bring it in a nice shape. But for this we have to define for our program the coordinate axis. And let's say I want to define that the span direction of the membranes is going in this ray definition, and let's say the orthogonal definition should go around in a circle. So for this, we open the properties of the surface. So I select these surfaces for the right cone, go into the properties, surface, edit, open the option specific axis, and define here direct to point, and pick here the center 2 times. I get here the same point at the same, and I only change here one coordinate to 0 so that I can define an axis in between, and everything is clarified. For the left cone, we do the same. Right click, surface, edit, specific axis, input axis, direct to point, X is the span, should show to the axis, and we pick 2 times the center and changing one coordinate. Go, and now the last one, it's this part plus this surface. Right click, surface, edit, and let's open the specific axis and do this step last. Run 2 times and 0. So now we defined the axis of this structure. Yeah. In the next step, we should take care about boundaries to support this structure. So what we saw, we have in our model here these, let's say, span cables around. So let's define these cables. What means we go back here, make a top view. If you want to change the view, you can only write the letters inside and the program is rotating. So here we can select all lines around by pressing the Control key. You can select all in one. Right click, edit lines, and now let's say we assign to this line a member stiffness. This should be a cable what can only take over normal axis forces, and the cross section is a cable. So for example here this PE20 cable with a diameter of 16.6 millimeters with a equivalent stiffness. Yeah, and if I confirm this, the program draws this line, let's say in a different color, that we see, okay, here is defined something. So the other boundary is, let's say, the fixation of the heads and bottoms of the cones. Yeah, of course, here could be constructed some wheel or whatever. So I'm not interested in this, so I replace it by a rigid surface. So I open here option, stiffness type rigid, and let's say bring in here such a wheel plane what connects all lines around. The same here. So let's define the boundaries, and now the last one, and you see it's quite easy. Now, of course, this plane is not rigid, it's only inside the model, so we have to fixate it that we have boundaries. So we fix this node. So let's define here a node in the middle and say, okay, we have here, for example, a rigid support. Something like the membrane is connected to the bottom plate. For the cable, what is running around, we have, let's say, a fixation of these markant points where this structure is connected to the primary reinforced concrete structure, for example, what is created here. But we replace it. So now what is remaining? So we have now supported the cable. Here's one missing, so let's copy it here. So we have here this supports roundabout. We have supported the funnel on the bottom. Now it's remaining the two cones. So because it should be supported at this point. So how we can do this? I would say we can model in something like this steel frame. So, oops, I want to show you this steel frame here. So, how we can do this? So let's look inside the structure. For this, maybe what could be interesting for you, we have these clipping planes where you can go through this model. Of course, this gray view is not so nice, but if you don't need it, you can deactivate it, and you can say also here, please don't show clipped areas. So you can directly watch inside. And here we need a supporting construction. So let's say here, for example, here we have a line, and also here. Oh, here you see I don't pick the line, so let's move it here. And now let's select these lines and copy it one story down. And now we can specify, okay, this and this line should hold a cross section. So we edit it, we assign a member, and no cable in this type we select a beam what can take over all this type of forces, bending, normal, torsion, and so on. And we specify, yes, we want to apply here a circular hollow section with a diameter of 250, thickness of 5 millimeter. Yes, and this cross section we assign to this line and confirm it, and you see now we have a support of this cone, and the only thing what is missing is here a support to the foundation. We simulate it with a fixed support. Now it's ready, and we have our structure here. So in this point we are so ready that we can start calculation, and our first calculation job is that we find an optimal place for the finite elements on these surfaces what respects a specific pre-stress. And the pre-stress is already the keyword for the next task. So we define here a load case pre-stress. We do it without self-weight because the membrane itself has no big weight. And we specify here the yellow marked pre-stress. And now we can give the program the information which pre-stress we want. Yeah? And for this, we select this first part of surfaces. We open the surface loads and specify here the type form finding. And we type here the type projection for these radial shapes with stabilization. And we specify in X, so the axis what is running from bottom to top, 1 kilonewton, and the tangential 1 kilonewton, for example, but you can change it as you want. Now we say, okay, this definition of pre-stress in this radial construction should follow a rotation axis what is running through, let's say, this point, and confirm it. In the next point we do the another level, so we say it should run through this point and should be valid for this surface selection, and confirm it. And now as last we do it for this axis what is running through this point and this axis, and it's valid for this surface selection plus this surface, and go. Now we specified on every surface part a pre-stress scheme. You see every field is selected, and what is missing is, let's say, the description of the cable. So at the moment the cable only knows I'm running from between these green points, but if we hold it straight it will get a really huge force, so a sag would be helpful. So we can define here a sag. The only point what is strange is we have here divided cable because this surface distribution. So I would, let's say, merge these two cables together, and we can do this with a member set. So let's select it, and now I think it's easy to do everything with member sets. So I select more members, always with a gap in between, because if I select everything together, the program thinks the full cable, the full member chain should be one member set. In this case, when I say here, please create a member set, the program recognizes 6 elements, what is fine. And now we can do the remaining again with a gap in between. Right click. Oh, it's only 5. Why? Because here is no cable. I think here is a cable missing. Cable section, here this one. Yes. Okay. And now again, select it here, 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 and the last one. And now if we select create member set, we get 6 more. And the program defined us here now below member sets 6 elements. And now it's easy because I go into member loads, not member loads. We go to member set load, load type, from finding. Geometric is okay. We want to have a sag, maybe with a 0.5 meter sag under tension. And now we can easily draw a window about the complete structure because we know we have 12 member sets. And with confirmation, now the member set gets this definition. So now we are ready to do our first run. And this means if I run the analysis, we directly see if the program can mesh the structure, if we find the equilibrium, if we did all inputs, so if something reacts strange, but it seems quite well and we get a result. So it seems in the first point of view good, but our next task is now to check the plausibility what we did. So of course 2 cones seems reasonable. Curve seems reasonable. Question appears why it's here red and the rest is blue, why we have here such a big deformation and here no. Why? The answer is easy. If we do the deformation plot on factor 1, you see the result is drawn on, let's say, the mesh. And if I say, hey, this program show me the original shape, you see this is what we defined initially, quite rough. And the form finding algorithm in background have to find now a good shape, and you have to move these mesh elements here to the bottom, so to the deformed shape. And you see, okay, these elements have to go the fastest way, and for this, for example, not zephyr, we have here color distribution. But this is only the movement from the original mesh. This is the shape what the program is found. Visualization of the coordinate. Yeah, looks quite homogeneous. What we expect, we get here forces. So for example, the span from bottom to top is running from 1 to 3.3 and it increased on the cone. What is quite clear because the effective width is smaller. The tangential forces around the cones is running homogeneous around cones, so this distribution looks clear and it's running from 0.3 to 1. Also, okay, I would say. Then from forces, so if we take a look on, maybe hide the mesh, if we take a look on the deflection of cables, you see we have an inside ward deflection like an arc, like a banana. So also clear. We have here dimension smaller than 0.5 is also clear because we have here, let's say, this is the component in Z direction, this is the component in Y direction. Both together represent the 0.5 meters. The cables have a positive tension force, they're drawn in red. The column have a drawn in blue normal axis force, have a compression, also clear. Yeah. And according to this, we get also a bending. So result looks more or less reasonable, but, and now we come to our stages topic, what was the second word in header of this webinar. We get a situation that the owner of the structure, for example, ask us engineers, hey, can we change it somehow that I have more space here in bottom? So when I watch, for example, I turn off the results and I view, you see, let's say drone mode here. When I'm here standing below, so standing below my structure, the columns are disturbing me. Yeah. So is it possible for you to do it without this steel frame inside the structure? And of course we can do. The only point is what we should consider. We have forces in this structure already. So So if I watch results, there are forces inside the structure and we have to consider it. And they are memorized somehow. And the question is, are there any tools to do this? And I can recommend you here the stages application, what allows us to take over memorized forces into a next stage. For this, we have to model the additional supporting construction. So let's do this. So let's make here, replace this frame or draw additional. So I draw here node between lines, pick these two nodes, confirm, yeah, apply, and now use here this grid point plane and place it here inside this frame. Now we can watch in Y direction, and let's say we can draw here such an arc, for example, like you saw in the picture here. Yeah? And for this, I use here an arc or maybe a parabol, and we can pick it here and make a height of 10 meters and maybe this node. And you see, principally fine, but we have here intersection, so maybe move it 1 meter into right direction, and you see, okay, intersection is closed. And now we can take this as beam and can hang the cone peaks on this arc. Yeah? And now let's go ahead and assign to this arc here cross section, and because it remembers me to an old business trip I was in St. Louis, where is something also such an arc, and it was from a huge triangle cross section, and I tried to simulate this in RFEM also. So let's go into the properties of this arc. Properties, go to main, go to member. This means we assign a member. It should be a beam, of course, and the cross section should be a new cross section. Yeah. So program select something from standard, but we say we want to have here a user-defined cross section. This triangle cross section, what I mentioned, the hollow section from triangle shape, not the circular, and a triangle hollow section. Yeah. So the program opens a section live from RFEM, what allows us to model here a user-defined section in time. So this was the standard settings, this IP80, so we can delete it. And let's model here the section what this arc should get. So let's make the same like in begin, such a triangle with same angle. So we rotate it by 30 degree and rotate it back with a copy by -60. Okay, close the gap with a new line. And now we have 3 lines. And here's a pretty cool function. We can use here create element on lines. So I select these lines with a thickness of 20 millimeters for steel S235. Confirm it, the program defines it, and we can, without calculation, so we say save and return, and the program is moving this triangle into RFEM for further calculation, updates the stiffness, all these values, assigns a material, and with OK, and OK, of course, the result deletion, we get this triangle here in our structure. Yeah. So maybe here you see it a little bit better. Yeah. Now we can go ahead and can say now we hang the structure on the cones here. We copy these elements, intersect it with the arc. Yeah. The remaining element we delete, and this looks a little bit massive. So let's change it to a member edit to a truss thin or a thin truss beam. So let's take here truss section, a new section, go to library, go to solid section, maybe round bars with a 20 millimeter diameter. Yeah, and confirms this. So now it looks quite slender, looking good. So the only thing what is missing is the support. So we support the arc. And now we could be ready for calculation. And of course, we can start calculation. What means when we run this analysis, we will get a multicolored picture, of course. The question is if it's right or not, because we don't have both structures together from start. So we get here forces. Yeah. But what is really interesting is if you watch, for example, these forces on this beam, so you get here now a mixture. So the arc is taking over something and the columns is taking over something. And this is not real because when this structure begin to life, it have only this columns and no arc. So the main force is in columns here. And this is directly the point where you need a stage. Yeah? And for starting with stages, we go to the navigator. You will see here a special icon, construction stages, and we can say new stage. And we say the stage is consisting from members, from surfaces, and from nodal supports. For members, we can say what is active in the first stage. So I would say everything what is maybe here inside this window here. Yeah. Yeah. And for surfaces, the same. Everything what is inside this window. And for nodal supports, also the same. Everything what is inside this window. Yeah. And if we confirm it and watch it here, construction states, you see, perfect. Now I see my good old structure not calculated. So let's calculate it because strange, I can calculate the stage. I'm expected what will come out here, out of this calculation, and you get nothing. You get the sharp edge model. Looks strange, looks like wrong. No, it is not wrong because this construction stage, of course, have to know what is its loading. So we have to go to the load combination rule, and you have here construction stages. Here's one, and it's empty. So we have to move this pre-stress. And maybe to be consequent, we need also a load case. So let's say here, maybe a permanent self-weight load case. Here we activate the self-weight, and we can also throw in this G load case. Well, and if I run this again, this load case, you will see the program will get the initial calculation what we did first with load case 1, more or less. Yeah, we get this red flag here, we get column force almost 25 kilonewtons, we get this maybe membrane tension from 1 to 3.4, 3.3, and we get here from the tangential force from 0.3 to 1. Yeah, so it's the initial model with the stress state. And now we can say, hey, there will be a rechange, so we can make a next stage. Yeah, we can say, okay, new construction stage consisting all elements what we have plus. Yeah, so oh, this should not be. I think this is connected to this webinar application. Let's start again. So, and here it is. So console, we open VWT6. Here we ended. So we was on construction stage 2. Create new construction stage. Add this member, this member, this member, and this small thin trusses. Okay, and add here this nodal support and this nodal support, and go from forces. Let's say we check it, construction stage. We have now here the second, but it already have eaten this load case from the previous. So let's say this is not a problem. So to get results from construction stage 2, we have to calculate 1 at first. And now you see, so this was the start. Oops. This was the start. And now we add this arc, and you will see now these hangers have more or less nothing inside, only some effects from surf weight, and we have still here this 25 kilonewtons, and the membrane itself have here maybe 1 to 3.4 and tangential 0.3 to 1. So this remains, yeah? And the arc is not loaded highly because it's only the surf weight itself, no? But in the next point, we should consider how we can replace the steel frame inside, because it have here a high load on it. So this means, I would say, we add a load case, new load case, and we add here maybe a press, permanent load case, and say here, for example, this is an imposed nodal deformation, and I lift it with -2 millimeters. So I press up this steel arc with 2 millimeters upwards in a new stage. So we make here new stage. Everything remains. So this stage 3 remains on 2. And for loading, yeah, we say construction stage 3 should eat this load case 3 permanent. And then we calculate this stage. So CS2 is already here, so we have only to calculate CS3. You see, the big normal axis force disappears. Now the hangers take over because we have pressed up this frame, and now we have a big stress or force in the arc. And this is now the point where we can say, okay, let's remove this steel frame. So we go to stage, new stage, and now we remove, deactivate these inner beams. Yes. And nodal supports are already deactivated when I remove the beams. And okay. And now when I calculate the CS4, you should get the result without the inner steel frame, and the arc out on the outer side should take over everything. And you see now, okay, we have here this arc, we have here now the hangers, and the structure is supported and working. And now let's see results. So if we watch now results in membrane, you see, of course, the span direction not changed really much, so it's still from 1 to 3.4, but the tangential direction is a little bit crucial. So we are coming to small to 0, so 0.17 to 1. So of course we have no wrinkles, but you see the stiffness change of the arc have some effect on it, and you can now simulate with this technique such effects. Yeah. And this is now also the state where you can go ahead, you can consider new loads. So of course you to design such structures, you have to consider season, summer, winter, rain, snow, wind, a lot of forces. Yeah. I'm not able to model this now in this demo, but for me it's important to show you some highlights. And I modeled this structure with let's say with the background that I want to show you something. And what is for me quite interesting after these stages is that this structure have a funnel. Yeah. So this funnel here, if you imagine regarding snow and rain, it could sum up something, and this could destroy or hurt the structure. And we created in the development now a new function what should help you in this case. If you imagine it could rain, this funnel could be filled, and for this effect or action we created a load. And for this, let's create here a load case. So make a new load case, let's say rain. Give, for example, here this no item and confirm it. And now let's say rain should be on all these planes. So let's say surfaces, create the surface set. Okay. And now you see here basic objects where we have these member sets. We have also here a surface set. And let's open here a surface set load. And here we created a new option, ponding, what allows us to simulate a rain on a really slender structure. So we can consider the stiffness. So if it's rainy, the structure is changing and the sag is bigger. So this is a non-linear iterative load. And this you can consider in the calculation. So let's say we apply this fluid on this surface set. So symbol looks really crucial, but now we should say this load case 4 is acting on a specific, maybe on this CS4. So let's go to load case and combinations and say, okay, construction stage CS4 should work with this load case. But now you see this is not permanent and this is variable. This means it's something like a load combination. So let's check load combinations. And here you see generated load combinations in this purple color. Combinations with gamma factor, combinations without gamma factor. But if I click in, we have no initial state defined here. So maybe I want to learn you the connection. These load combinations are connected to this setting here, combination without. So if I deactivate it and delete it, we get no combinations. If I activate it, we get these combinations again. If I say in the design situations, we should work only with ULS setting, we get only these combinations with gamma factor. If I change it here to characteristic, we get the combinations without gamma factor. Yeah. But still no initial state. If I define in the wizard, I want to consider initial states and say which one. For example, only the construction stage 4 and confirm it. Of course, we need Newton-Raphson. We get here load combinations for CS4. Now it's filled for, let's say, permanent state and for permanent plus rain state. And this is now maybe the combination what considers the rain. It converged and it looks a little bit bulbous. If you take a look, what we see, these cones are sloped. This funnel is a little bit bulbous. And if you watch forces, you see this band direction have here really a high tension. So if you simulate it here, you see, okay, our stress layout is here with some peaks. The tangential force is here really high in the funnel. Yeah, why is this coming? It seems like filled. And this is in reality also the case. So if we take a look here on water level, you see the program filled this cone. If we watch it from the X view, you see he found a filled state until where the sag stops. So here the water could run over the structure, then it stopped raining to fill it. Yeah, and if you take a look on the water depth, you see, oh my God, we have here almost 5 meter water inside, so it's like a diving pool. Yeah. And this produce really high forces. Yeah, I think it's impossible to design it in this way, but 122. So we have to do something. Of course, we can start now thinking, do we have to fill it completely? Here's some drainage or whatever. Yes, it is. Yeah. And if you say, okay, I only want to check it until a specific level, you can do. So we have here in this ponding load, we have here in the ponding load function, read it, where you can define an amount of precipitation. For example, you want to consider 120 liter per square meter in a specific time. So you can write it down here. And after this amount of water, the drainage it, and I don't have to simulate the full filling of the cone. And let's confirm this and run it again. So CS4, run. Oh, not CS4. CS4 is only the structure itself. We need this load case with rain on CS4. And you see now the load picture changed a little bit. Now we have forces not 100 something and 22. And also the span is in reasonable forces. And if you take a look on the water level, you see, okay, it's not full, then something else. The water depth is saying us, okay, we have now a filling of 1.3 meters. This is quite interesting because you could ask now, why not 12 centimeters? Of course. But in this case, you have to know that this function is pretty smart. It considers the rain on the complete structure. And you have to know on this cone here, the water is running down to the sag, and on the other side, it's running down from the complete structure. And you can consider this effect, and this, let's say, surface part is consuming the water and the rest is losing it. So both effects are considered, and this makes it to a really strong tool. What I want to plan to show you, I hope I could inspire you a little bit. And now you can go ahead with other load types like wind, snow, and so on. Yeah. So this brings me also to the end of my demo, of the main demo. I closed it with this feature, and I want to go ahead with the point outlook. So you see we are still working hard on this field in our program, and right now to connect it with stages and to bring in some nonlinear loads. And at the moment, our team is working hard to finalize the cutting pattern tool to make a cutting pattern layout. And to be clear, these are no cutting lines for us, and this is a line what I defined in the original shape. So by defining this rough structure, for us is a cutting line that you cut the mesh after form finding according some conditions. And because we want to make it really efficient for you, we programmed it with some automatism now. So in future, you can define some master cutting lines on mesh and define a width of the material roll you expect or you can manufacture, and the program is detecting for you automatically the remaining cuts to reach a specific width of a roll of material. And let's say this is at the moment our biggest job in this field, and we try to finish it soon. And now I hope you enjoyed this webinar, and I give back to Jürgen.
Yes, thank you, Andreas. So before we leave, I will give you 1 or 2 hints. So I take back the control. So if you are now convinced by the software that you say, hey, these add-ons are great, I want to maybe test them by purchasing a rental license or maybe purchasing a full license, you can get in contact with our sales team and they will make you a tailor-made offer. And the second thing I want to show you is when I jump to our webpage, the www.dlubal.com, you can also browse at news and events. Under events, you can go to the webinar section. Here you can find all the upcoming webinars. So next week there will be another cross-section webinar about stress analysis in our section. And when I filter to the accomplished webinars, we will find our today's webinar, construction stages and membrane structures. And maybe 1 or 2 working days from now, you will find the recording of today's webinar. So if you have missed something or want to rewatch it, you can find it here. Yes, that's all from my side for now. Thank you very much for your attention. I would also like to ask you to stay within the webinar once I close it so you can fill out the evaluation form. Please have in mind that 5 is the best rating and 1 is the worst. So it's more like a star rating and not like a system of school marks. Yes, thank you again for watching. Have a great time and till next time. Goodbye.